Everyone, my name is Dr. Sia Makfeizi, and today I'm going to explain the principle of the effective stress, total stress, and pore water pressure in soil with a very simple words. I will not go through all details regarding in what they mean in theory, but I wanted to focus a little bit on what can we do through using these principles in the practical works. So it's just a small definition that I wanted to say that everybody maybe know, just a repetition, that the total stress is defined as the weight of the soil above the point that we are looking. So if we say that the total stress is the gamma, it is the density, the soil unit, times at the height of the soil. So if we have a soil here and the point here, then if we say that this one is h and the soil unit is gamma, so it is defined as a gamma h. So the pore pressure, and if in the same time we have also the water level at the same level as the ground, then at this point the pore pressure is the gamma water times at h. It's a static distribution of the pore pressure. But what means that in reality the effective stress or the total stress, if you wanted to say that, it is the sum of the effective stress and pore water pressure. So these three concepts are very important in the geotechnical design that I'm going to describe here. So the effective stress, if we just change the order of the values, it is the total stress minus the pore pressure, or in other words, the sigma prime is sigma minus 1 or minus u. So why it is important? The effective stress is important because if we have an overview of the effective stress at some layers, so for example, look at that one. If we look at the effective stress at this point and calculated the effective stress before and after activities, for example, in the ground, if we have a loading in the ground or whatever, we can predict that, okay, if the effective stress, for example, increase or decrease, do we expect any settlement, creep, consolidation, or any uphill? So it is the heave or settlement that it is the consequence of changing of the regime of the effective stress. So that's the reason that it is important. First, we don't include the effect of any external loads as it is here. It is above that one, so we don't include the external loads here. It's only now in this course, in this short course, we focus on the total effective and pore pressure only in the ground without having any external forces. But then in the next course I will go through that and describe a little bit more. So then if I go directly to the next slide that shows that the effective stress is the subtraction of the total stress minus the water pressure, and we know that the total stresses, if we say that if the water, it is saturated situation, gamma sat minus times at h minus gamma water at h. So in the geotechnique we define this gamma sat minus gamma water as the gamma sub, or you can just say that it is the gamma prime. It is the same word, maybe it is gamma prime times h could be used. So submerged weight at the h if there is no seepage or leakage, that which I'm going to talk about in this slide. So this slide number 1, if we have the soil, if we have the, for example, homogeneous soil, and we have the groundwater way below the area that it is our interest. So if we look at that point, and it is in an easy way that we can say that the sigma I, there is nothing above the point A, it is 0. There is nothing with respect to the U, it is 0. And then we can conclude that the sigma prime A, which is the sigma A minus U, is 0. So that's the easy check for the point A. Then we go to the point C. If we go to the point C, sigma at point C is that the weight of the soil. So it is the gamma, it is the soil unit times at this edge. U at this point is equal to 0 because the water is located here. We have a dry condition at that area. So we don't have any soil or we don't have any water. And based on this, we can say that the sigma prime C at this point, it is gamma h minus 0. So it will come to the gamma h. So it means that when it is the dry condition, the total stress and the effective stress are the same. So it is easy even if we just put a chart. So if we have a line here, we can say that it is 0 here, the sigma A is 0 to gamma h. So this is like as this linear distribution that we can, and this is valid for both effective stress. So this is a gamma h. So this is the valid for effective stress and total stress. But not most of the times we have a dry condition. So in some cases we have the groundwater. So if we have a groundwater, what happens? So then again, we just go and continue with what the principle says. At point A, it's the sigma A is 0. U is 0 because the point A is above the groundwater. And then sigma prime A equals 0 because it is 0 minus 0. So this is for the point A. So if we go for the point B, it's a bit different story. So sigma B is equal to the weight of the soil above, which is here, which is the gamma at that area times at H1. U still at this point is 0 because the water started from here and then it is 0. And sigma prime B is equal to gamma H1 minus 0. So then it is the gamma H1. Then we go to the point C. If we go to the point C, what can we see here? So the point C is an interesting point. So we have, if we look at above this point C, we see that we have an area here which is inside the water, and we have an area here that it is the dry. So then it is the condition that we should consider, these two conditions. So then for point C, maybe I should write at this part, at the left part where I have a bigger space. So then for point C, if I write that one, then it is this area which is the dry. So it is the gamma times H1 plus, and the gamma at this point, which is the gamma, again the same soil, times at H2. And while these two gamma, or it is a homogeneous soil, we can say that gamma at H1 plus H2, which is the gamma H. So we can say that at this point also it is the gamma times at H, it is the total stress. But how about the water pressure? Water pressure is, again, it is from the start point, which is from B to C. So the height is H2. So we can say that it is the gamma water times H2 is representative of the pore pressure. And what is about the sigma prime at point C, which is the subtraction of the total and the pore pressure. So if we write that one, so it is the gamma H1 plus gamma H2 minus gamma water H2. So if I just write that one, gamma H1 plus, and if I take the same H2 here, so I can write that from this one and this one, gamma water minus gamma water here times H2. And then we know that if we write it in a better way, so it is the gamma H1 plus, and we know that gamma minus gamma water, we can title it as a gamma prime submerged times H2. So that's interesting. So for point C, if we wanted to calculate the total stress, effective stress, and pore pressure, we should be careful. At point C, then it is the total stress, it is very easy. So then it is according to what it is the gamma times H. The pore pressure, it is the gamma H2, and the effective stress, it is the combination of two components. It is here, it is the dry, we can say that it is gamma times H plus, at this point, we have to use the submerged weight because there is water here. So it is the gamma minus gamma water, which is the gamma prime times H2. So actually, this one is sigma, this one is U, and this one is sigma prime as highlighted here. So if we just subtract this one with that one, we will get this one. So this is the case that actually we have no seepage and we have a water in the system. And I want to maybe illustrate it with some simple example that make be easy for everyone. So if I come back again to a other file, then I just draw a line here, a little bit, I put 3 layers. Here it is, for example, 2 meter, and here I just put, for example, 4 meter. And the gamma, it is the sand here. We have a sand layer here, it is the clay layer. The gamma is, for example, 19, and the gamma is here is 18 kilonewton per cubic meter. For both is the same unit. So if I look at the water level, they say that the water is located exactly at this interface between the two layers. So if we say that it is the water here, and then we calculate the stress point at A, at B, and at C, how it will be. So just for A, it is very easy. Everything is 0. It doesn't matter. For at point B, I calculated the sigma B equals 2 because we only have the sand above. It is the 19 times 2. So it is 38 kilopascal. And the U at point B equal to 0 because we don't have any U there. And then the sigma prime at point B, then it is 38 minus 0, so it will be 38 again kilopascal. This is the first point. So if I go and look at the point C, if I take it down, and if I at point look at point C, so at point C, the sigma at point C is combination of two components. It's 19 times 2 plus 18 times 4. So this one is 3080 and this one is 72. And this one is 110 kilopascal. U at point C is equal to the height of the water here, which is 4 meters. So the gamma water, this one is the gamma water, which we know that it is 10 times at 4, it is 40 kilopascal. And then sigma prime C at this point is 110 minus 40. So it will be 70 kilopascal. And then in many cases, it is easier to illustrate them in diagrams. So if we say that This is point A, this is point B, and this is point C. We know that nothing at point A, it is everything. If we just plot the sigma prime, it is 0 here. At point B, we calculated the effective stress and total stress is the same, so it is the 38. And at point C, we calculated that it is 70 kilopascal, so it is here. So the diagram is like that one. And this diagram is important because when we have this diagram, it is possible to calculate the total force. This is important for the retaining wall and other issues that I'm going to take in the next lectures. I hope that this clarification was simple enough for many of you. In the next lesson, I'm going to talk a little bit about that if we have the seepage in the water, because in the old case, we didn't have the seepage, so we calculated everything if there are no seepage. It means that if I had a piezometer at point B, if we have a groundwater here, if I have a piezometer here at point B and at point C, the water goes up here and it is exactly the same level that I have in this point. So in this point and in this point, they are at the same level. So there is no flow going between C and B. But if I put a piezometer at point C and the water level here, so it means that the flow can just go from here, from point C to above. And that is the seepage upward. And if we have a case that the piezometer shows the level of the water is below the point B, the flow can start from B to the C side. In both cases, then the formulation that I have given here, sigma prime minus sigma prime equals to sigma minus 1, is not valid. And then we have to include also the flow effect on that one. And the principle and description of the hydraulic gradient and those things will come in the next lesson. Thanks for watching the video. I hope that you subscribe this channel, and from now on it will be more lesson and technical and practical items in a short time. And thanks for your patience and attention.